Today I'll tell you about environmental project and second, research strategies to detection. First is environmental project. Many goals develop circuits for receiving signals from the environmental sensors. Sensors can sense temperature, humidity, a lot of gases like SO, CO, CO2, carbon dioxide, carbon monoxide, and we can detect dust and cigarette smoke. Sensors may require low-pass filters and converters, but we are happy we have 18MB128 microcontroller, which has an electro-digital converter with a low-pass filter and amplifier. And resistors are needed between controller pins and circuit elements to prevent burning of the pins to decrease the current. And microcontroller should process all the data received from the sensors. And next step, after we sense all the data, we should create wireless network between sensor nodes. We're going to put sensor nodes in different places and receive data from different places to make kind of statistics, to gather statistical information. And I'm going to make wireless communication between sensor nodes and main computer, which will process all the data. And final step of project is to mount sensor nodes on static and dynamic objects. We should develop autonomous static sensor system for long-time environment condition observations. And second is to mount sensor node on flying machine like multicopter and on ISLab golf cart for detection of air quality around some region of interest. Which hardware I'm using? I'm using 18MB128 microcontroller, which can work with very fast, 16 million instructions per second. We use crystal, 16 MHz crystal. And it contains 128 kilobytes in system memory. That allows us to use C language, which is much easier for programming than assembly language. And I'm using SHT71 temperature and humidity sensor. This sensor gives us digital signal, not digital signal with just numbers. So we can easily gather information from sensor, and this sensor contains microcontroller. So we don't need to use low-pass filters or something else. And I'm using LCD display to make standalone sensor nodes which can work without computer and which will show temperature and humidity information. And I'm going to use 18MB wireless communication unit, which consists of microcontroller and transceiver. And ISLab company provides software for this sensor communication unit, so it will decrease the development time of wireless network. And this transceiver can work in ZigBee networks, so we can make mesh networks, high-level networks. And I'm going to use SP3S gas sensor, which can detect concentration of ethanol, hydrogen, carbon monoxide, carbon dioxide, isobutane, methane. And we are going to use smoke and dust sensors, but this sensor, Jan Fei, my co-creator, he uses this sensor. Me and Jan Fei will make the same project together. I'm developing circuits in hotel software. This software allows me to simulate this circuit without creating a real one. Before creating a real one, in order to prevent burning of real hardware. In my circuit, I'm using external generator which increases performance to 16 million instructions per second, because building crystal works with 1 megahertz on the frequency, but I'm using 16 megahertz frequency. And I'm using LCD for standalone indication, temperature and humidity, and in the future we can show more information in this LCD. And comparing to 7 segments displays, this LCD needs only 1 port for function, but if you use 7 segments, you need more ports. And all the sensor data processed by microcontroller, and this is my sensor in Hotel's software. I can change temperature, and I can upload real program, real firmware to this microcontroller and simulate how it works. And after I made all the simulations, I added resistors to each pin to prevent burning of pins of microcontroller. And then I created, with the help of Andy, a real circuit which contains LCD, microcontroller, and ADR, and temperature and humidity sensor. And I tested this sensor, and it showed real temperature and humidity. It was close to reality. So I created virtual circuit and real circuit and made tests. For sensing data, I used improved temperature and humidity compensation formulas. These formulas were given by creators of sensor. They increase accuracy due to non-linearity coefficients. So characteristics of sensor cannot be linear, so we need to compensate non-linearity. So I'm using these coefficients which were given by creators of sensor, and tests show that sensor gives real information using these coefficients, and it decreases error to 0.1%. I made program in using C language and AVR Studio IDE. So it allowed me to make program in short time, and program implementation consists of next steps. I initialize LCD first and initialize sensor, and then I have small delay, and then read data from sensor and apply the temperature and humidity compensation formulas that I showed in the previous page, and show temperature and humidity data on LCD. Then I have delay for 500 milliseconds to prevent self-heating of sensor. Because if I gather data more frequently, the sensor will show not real temperature, but the temperature will be increased by self-heating of the sensor. I'm going to use sensor network. I'm choosing between star topology sensor network and mesh topology. Advantages star topology is we have one data handler and sensor nodes which can communicate directly to the data handler. We could use this topology if we had communication transceivers which can work within maybe 1 kilometer or 2 kilometers. In order to use these transceivers, we had to use 900 megahertz. But in Korea, we cannot use this frequency without band license. So if we cannot use this frequency, we should use 2.4 gigahertz transceivers, but the operation range is maybe 100 meters and no more. If we can buy license, we can use this topology network. Advantage: a single hop approach for communicating between each sensor module, and the base station results in lowest overall power consumption. This is, I think, it's an important part for standalone applications for long time sensing. But disadvantage: operation distances are limited. 2 kilometers for 900 megahertz transceivers and 100 meters for 2.4 gigahertz transceivers. If we use 2.4 gigahertz transceiver, which works in ISLab frequency, which doesn't require license, we should use web topology network or mesh topology network. In this network, we have data handler, but sensor nodes communicate between each other, and data handler, like PC, can communicate to each sensor sensor node. Advantages: long operating range, but we have a lot of disadvantages like possibilities of data loss and increases power consumption. And we should use media access control protocol. And we should use time division multiple access method to share the medium, to share the same frequency. So each sensor node can work only in each period of time. So if you use a lot of sensor nodes, each sensor node should wait for its order to send data. I think we'll use this protocol because we don't have to buy license for this frequency, 2.4 gigahertz. Summary. I provided circuit simulations in hotels, and I created a real circuit and provided real tests, and wrote firmware and tested it and future works. I'm going to develop circuits for other environmental sensors with the help of Yanfei, and create firmware for new sensors and make simulation of hotels. And next I will develop sensor network and try to create control program and graphical user interface for personal computer and maybe for Android devices, for mobile devices. And I'm going to mount sensor nodes on car and multicopter and provide new tests, like dynamic tests. Next research is traffic density detection. So the goal of this research is to detect type of cars and then number of cars on the roads using laser radar. It's called LiDAR. Quality of existing illumination doesn't affect recognition performance for radar, and LiDAR is able to detect objects through rain, snow, smoke, and fog, which camera cannot do. And how to do it? I'm going to create software based on one of modern programming languages. Now, MATLAB interface exists to LiDAR, but MATLAB works much slowly than any of modern programming languages. And MATLAB requires expensive license. And I'm going to create mounting frame which allows to provide outdoor tests. I will use durable metal components which guarantee safety of using LiDAR in real tests. This is design of mounting frame. This is LiDAR, and this is metal bars, which load capacity is about 500 kilograms. So it's really reliable frame.
500 grams.
500 kilograms.
500 grams?
Kilograms.
500 kilograms.
Yes. I'm going to make some simulation in SolidWorks to prove its durability.
You said 500 kilograms?
Yes.
On weight?
Yes, this. this can work with what 500 kilometers.
You mean stress?
Yes, yes. But weight of lasers 13 kilograms or less. Let's do the first. I'm using these bars because we have these bars already in the laboratory. And I'm going to provide first test on the bridge above the road. So height of bridge is 5 meters and length of 2 lanes is 6 meters. I'm going to mount LiDAR here, and it will scan 60 degrees plane, like cone, 60 degrees. I'm going to place in real world. I'm going to place the LiDAR here. It's close to our school and place of testing here. So we don't have to spend a lot of time to reach the testing site. Test site. How to detect the height and distance to car, and on which line is the car we should use, or these two formulas. We know the angle of the laser, and we know the distance between LiDAR and some obstacle. So we can use formula for detection height to the car and distance from the sensor control. Is that line or other line? We have two lines, first line or second line on the road. After we measure distance, vertical distance, 5 meters, 5 meters, 4, 3.6, and so on, we can guess shape of car, and using shape of car, we can guess type of car. Is it passenger car, or bus, or truck? Consider LiDAR performance for extreme case for 200 kilometers and very small car, like 3 meters long car. We need 18.5 scans per second to get at least one slice of the car. We have stick LiDAR which can give 75 slices per second and scans per second, and it will give 4 slices of each car. I think it's enough for us to guess the shape of the car. And minimal distance with speed between cars should be at least 75 centimeters. I think no one will run so close with so high speed. So we can use our stick LiDAR for our tests. Summary. This research topic was chosen in order to make research about environmental sensors, but I'll do it on spring. And LiDAR will be used for traffic density detection. I decided to use Python language for first tests as fast enough cross-platform language. I can use this language on Linux or on Windows, and this is free language. It requires no license. It works under GPL license, and feature works. I will mount frame. Mount frame should be created and reliability should be tested in SolidWorks. And I'll draw up algorithm for reliable cars number and type detection. And this is my schedule for next year. I'm going to finish working with sensors on July. First step will be finished on March. First step is gathering information, reliable gathering information from each sensor and making outdoor tests. Second step will be finished in July. It's making sensor networks and making graphical user interface for PC. And I have my full project, and I will start traffic density recognition using LiDAR on May. And I'm going to finish everything until the year will be finished.
Question?
That's all.